All right, so thank you all for joining to this new Continual AI Reading Group session. Today we have the pleasure to host Jeremias Knoblauch, and he's going to talk about his recent work, Optimal Continual Learning as Perfect Memory, and his NP-Hardness. So thank you, Jeremias, for joining us today, and you can start presenting your work now.
Thank you very much, Vincenzo. I hope I pronounced that correctly. Thanks for the invitation, and thank you all for being here. So this work is published at ICML this year, and a version of this talk, I should mention, is actually already on YouTube. So if anything's unclear, you can go back to that. But more importantly, you should really use the opportunity of having me present here to interrupt me and ask me questions at any time today to get the most out of the session for yourself. So this work is called Optimal Continual Learning, has perfect memory and is NP-Hard, because these are the things we show. And when I say optimal continual learning, what I mean is continual learning that does not suffer catastrophic forgetting in a way that I'll obviously define more concisely later on. This is joint work with these lovely gentlemen that you see on the slide here. To the left, you have Hisham, who's a brilliant mathematician currently based in Australia. And to the right, you have Tom, who's working at Amazon in the UK. Okay, so the way I'm going to structure this is that first, I give you sort of the rough outline, the big ideas that we showed to be true in this paper on 3 slides. And then I'll give a formal outline of how we're going to go through these things. And I think to summarize, to take away everything I'm going to explain in more detail next, summarize the 2 things we really do is we connect the notion of catastrophic forgetting in continual learning to set theory. And you can actually do this fairly straightforwardly. And when you do this, you then get the power to show 2 fundamental computational properties of any continual learning algorithm that does not suffer catastrophic forgetting. And these properties are NP-Hardness, which is a notion from complexity theory I'm sure you're all familiar with. And the other one is perfect memory. In order for that one to make sense, you need to define a few more things, but we'll get to that in due course. And once you can show these 2 things, there are 2 main practical ramifications that I'm sure a lot of you are interested in. The first of which is that regardless of how smart you choose your continual learning algorithm to be, regardless of how refined it is or inspired or biology or whatever it is that you're doing, ultimately, it is a heuristic polynomial time algorithm attempting to solve an NP-hard problem. And so in general, what that means, it's going to be hard and you should expect failure. And in fact, if you don't get failure, that is in itself remarkable. And the second part is that the memorization aspect of our findings, so the fact that optimal continual learning hinges on the need of perfect memory, should tell you that memorization strategies should be expected in general to work better than regularization strategies, because they sort of mimic the perfect memory that you would need to design a flawless continual learning algorithm. And the device by which we will make all these conclusions is set theory. And here I've drawn you a picture that will probably, I think it's in the presentation 2 or 3 times, because it is that important for what we're doing. So it makes sense to pause a second and think about this in a bit more detail. Can you actually see the mouse if I'm waving it around? Is that on the screen?
Yes, we can see that.
Fantastic. So I'll probably do a lot of waving around with the mouse, because usually I would use my hands. I'm very Italian in that way. So what we have here is we have a sequence of sets, and these sets are actually defined in relationship to tasks. And in particular, what these sets are, they're the set of all parameter values. So you can think of them as the set of all models, all hypotheses, all parameters, whatever terminology you prefer, such that a given criterion that you want your algorithm to possess is satisfied on that particular task. So let's say some error, for example, some absolute bound on the error that is satisfied on all parameter values in this set. And we call these sets satisfiability sets because your optimality criterion is satisfied on these. And what you can essentially show is that an algorithm that does not suffer catastrophic forgetting has to follow a sequence of intersections of such sets, right? Because after the first task, you want to be anywhere in this first set. But then as you move to the second task, you need to not only be in the first satisfiability set, but also in the second one, which tells you that you're also not making a too big error on the second set, and so forth and so forth. And as you move forwards through your sequence of tasks, you're essentially forced into having parameter values or models that are in smaller and smaller intersecting spaces. And that is the main intuition underlying most of the work that you're going to hear about today. One other intuitive device that's very useful throughout is to think of continual learning as an exponentially growing tree. Because at each time point, when I say time point, what I mean at each task, you do not yet know what task you're going to encounter next. So what that means is all the solutions that work on the first task sort of have to be memorized until you can be sure of the ones that you can discard because they don't work anymore on the second task. And so you need to navigate a kind of tree structure that forces you at each time point to memorize all working solutions that happened before, because you can never be sure that the next task wouldn't require you to use a solution that you have discarded before you saw it. So that's a very convoluted way of saying the very nature of the problem won't permit you to throw away information other than information that's not already in the intersection of satisfiability sets. And so in essence, what we can show formally is that your algorithm always, at each time point, needs to memorize the entire intersection set, because anything smaller than that runs the danger of then not working anymore in the future. Okay, so these are the sort of big ideas that I'll present today, and I'll try to do that in 3 steps. In the first step, we'll make this connection to set theory on which everything hinges more precise. And in particular, there's a formal lemma that shows you that you can do this, but I'm not going to trouble you with the lemma. I'm just going to go into more detail and introduce a notation that we're going to use. In the second step, I'll explain the hardness result, which actually is the easier result to show. Because in essence, the hardness result boils down to saying, if you have 2 sets, you want to find their intersection, but you don't have one of those sets, then you can't find the intersection. That's a simplistic way of phrasing it, but that really is the underlying logic. And the second part is the perfect memory result, which is actually, in my mind, is more interesting because it's more practically relevant for a lot of the continual learning algorithms that are being designed. And here, the idea is to show that for each class of parameters that would give you the same input-output relationship, you have to store at least one of these in order to not suffer catastrophic forgetting. And of course, we need to define perfect memory first and all that, but we'll get to that. And I'll talk very briefly about the practical ramifications, though I think most of you will be more suited to talk about that. And maybe that's a very good segue as well towards the discussion, because I myself, I'm not working on practical algorithms for continual learning. So it would be interesting to hear your thoughts and your input at the end of this as well. Okay, so before we move on, let's first define the notions that we'll be operating with. I mean, you're all familiar with continual learning. I don't have to explain continual learning. What I do have to explain is the theoretical framework we're working with here. So at each task, we will consider the model that we learn, or the representation in the hypothesis space that we find to suit the first task. We'll call that θ1. And because in continual learning, we often pass additional information through time. In the paper, we actually allow for additional information, which we call I1. So you may collect gradient information, or you may store some examples from the first data set as well. All of that counts as information. And you're allowed at the second task to take into account the data relating to the second task, the parameter value θ1, and the information I1. And you're allowed to, after you've done your inference or estimation procedure for the best parameter value θ2, you're allowed to pass on θ2 and I2, which is the information extracted from the second task, to do the same thing in the third task. So in that sense, we're giving the entire thing a Markovian structure, or a recurrence relationship, if you so will. And a lot of the proofs we do of course, make use of this recurrence relationship under the hood, though you won't see a lot of that. But it's essential to define things in this way for what I'm going to show you to work. But what I will say is that it's not very restrictive to define things in this way, because you could always include more in the information. I mean, this definition of continual learning in principle it would allow for perfect memory. You can in principle include all your data observed in task 1 into I1, and then all the data you observe in task 2 in I2, and so forth. So this is a very general definition. Okay, and just in order to stick a bit with the notation, theta t will always refer to the parameter value or the model that you select after you've observed t tasks. So ideally you would want theta t to perform well on tasks 1, 2, 3 up until t. Calligraphy q, that's going to be the set of tasks you can encounter, which of course in practice they'll be unknown to you, but because we need the mathematical device, we just specify a set of distributions. And typically in this presentation, I will be considering empirical distributions. So these are the distributions we consider, because mostly these are the ones you will be working with in practice, but our analysis actually isn't restricted to that. So you could even be considering continuous value distributions. The same results would still hold. The most important part maybe is the optimality criterion. So in order for you to know whether or not your algorithms actually suffered catastrophic forgetting, you first need to know when it hasn't suffered catastrophic forgetting. And so you need to define some optimality criterion that tells you, yes or no, I have suffered catastrophic forgetting on this task. And so, for example, and this is going to be an example that's sort of recurrent throughout the presentation, in a linear model, you could consider an epsilon upper error bound. So you could just consider the prediction error you make with a linear model and say, well, if that's larger than epsilon, then my criteria is violated. So I'll classify that as catastrophic forgetting, and otherwise I'm happy with the performance of my algorithm. Of course, much more sophisticated optimality criteria can be drafted up. This is just an example to give you the idea. And if you have defined this optimality criterion, you can actually define these satisfiability sets extremely easily, because you can just say, well, it's all the parameter values for which this optimality criterion equals 1, aka where this optimality criterion is not violated. And once you have all this stuff in place, it becomes very easy to actually define what no catastrophic forgetting means. It means optimality on all tasks. And by definition, optimality on all tasks just means that theta t needs to be in the intersection of all the satisfiability sets that you observed previously. Right? And you need to formalize this intuition a bit. This is lemma 1 in the paper that I'm not going to bore you with. The important consequence of lemma 1 is that this picture is an adequate representation of continual learning, in the sense that this set theoretic interpretation for optimal continual learning is admissible. And so just to recap once again, this device, what it tells you is you have a distribution p hat 1, which that's our first task distribution. P hat 1, given our optimality criterion, induces a set on the parameter space, which is the yellow part here. And the second task we observe also induces a set on the parameter space. And the moment we move from the first task to the second, we're interested in shifting the model or the parameter value from a location that only satisfies the optimality criterion on the first set to one that also satisfies it on the second one, and so forth through time. And this is the set theoretic interpretation of continual learning. Okay, 1 second. Now, unfortunately, we need to introduce 2 more things for notation, but I promise, let me not promise, I think they're the last part. So the 2 more things we need to introduce are actually just collections of sets that we have already seen. So they're just for convenience. And in particular, the first one is just the set of all possible satisfiability sets. If you remember calligraphy Q, that was the set of all tasks we can encounter. And set T is the satisfiability set of the Tth task. So we're just writing set Q to be the set of all possible set T sets. So all possible satisfiability sets we could ever encounter, they're in this set Q set. And similarly, the sat intersection set gives you all the possible finite intersections that you can encounter by looking through the set sat Q. So we have 2 collections of sets, and we know from this picture what happens. We get at each time point an element from set Q, and we need to intersect it with previous intersections. So what we know is that optimal continual learning is computationally at least as hard as deciding whether or not there actually exists a parameter value in that intersection or not. Because for optimal continual learning, you need to find one of those parameter values. So deciding whether or not it even exists is less hard. You'll be familiar with this notion if you've run into complexity theory. It's usually called the decision version of an optimization problem. And so what we're saying here is that optimal continual learning is at least as hard as deciding whether the intersection between sets in these two collection of sets is empty or not, aka whether there exists a theta t or it doesn't. And well, with this in place, the first result actually follows pretty much immediately, because it's sort of well known that if the collection of sets is sufficiently complicated, and it really, when I say sufficiently complicated, I don't mean it has to be an extremely intricate shape or intricate geometry. Relatively simple sets will do. But the moment that is sufficiently complicated, intersecting these two sets and deciding whether or not their intersection is empty or not is already NP-hard. For example, it's NP-hard for the set of polytopes. And on this slide, I've somewhat redundantly plotted a number of polytopes for you to remind yourself what they are. They're just intersections of, they're just intersections of half spaces. That's all that polytopes are. And even these kind of simple sets will already make your problem NP-hard. What this means is the moment your algorithm is, or your model class is complicated enough to induce satisfiability sets that are at least as difficult as polytopes, you're screwed. And I think the next result I'll show you makes this more formal. But before we go to the next result, let's look at a simple example where already NP-hardness holds. So you don't need to have a complicated model to show NP-hardness of continual learning. Let's assume you want to learn continually with a linear model, right? So something that's actually should be straightforward. Turns out it's not. So here theta is a vector. It's just your regression vector, right? It's a coefficient it's a coefficient vector in a linear model. As before, our tasks are just empirical measures. Our criterion is the one that we used as an example earlier on, right? So we're just looking at the epsilon upper bound on the prediction error. And it actually turns out with this, you can already construct all polytopes in the parameter space. And what that tells you is that our result applies, right? Because the set of polytopes makes the intersection problem NP-hard. And so even if you were trying to do continual learning with a really, really simple model, you would be trying to solve an NP-hard problem. Yes, so this slide it basically tells you that if you're interested in using a more complicated model than a linear model, the sets that will be produced by your algorithm are necessarily even more difficult, right? So one way to think about this is a neural network can recover linear regression. So the sets that you can recover with a neural network will be strictly more complicated. There will be strictly more of them than there will be in the linear regression case. So that's why we have corollary 1 in the paper, which tells you that if the intersection problem posed by your algorithm is computationally as least as hard as for the collection of polytopes, then again, it's NP-hard. So in practice, that means that virtually all continual learning algorithms, or I should say all optimal continual learning algorithms of interest would be NP-hard. Okay, so that's the NP-hardness result. I think it might make sense for me to take a quick break here. And if any questions have accumulated over the last part, then it makes sense if you just blurt them out to me and I'll try to answer.
Yeah, Jeremias, we have a quick question on the chat, if you can see that.
Oh, I can't see the chat, sorry. I didn't open that one. I'm sorry, that is actually very smart.
No problem at all.
Will the satisfiability set grow if my model grows? Yes, so sorry, wrong correction. Will the satisfiability set grow? So the satisfiability set is actually a single satisfiability set is defined with respect to a single model, if you recall the definition. So implicitly, this definition of SAT-T actually depends on the model because your model depends on the parameter space. But let's say your parameters, so let's say you have model M1 and you have model M2. The parameter space for model M1 is smaller than for model M2. Then by definition of the satisfiability set, it grows in dimension, as in it's the same dimension of the parameter space. So if the dimension of the parameter space grows, then so does the dimension of the satisfiability set. Whether it grows in terms of the size that it takes in that space or volume, I think it's difficult to say in general. I wouldn't know. But what I can tell you is that if one of your models is a subset of the other, so if the model M2 that is larger actually encompasses model M1, then, and you use the same criterion, then by definition, the second one will indeed grow. So it's going to be larger. I hope that answers the question. Let me know if it's not clear and I can try to explain it a bit better. But are there any other questions? Okay, so I hope it was still understandable. But I'll continue, and please, if there are any questions at any point, just interrupt me.
Yes, thanks.
Okay, so the next part doesn't concern itself with the NP-Hardness anymore. Now we're actually looking at the memory requirement. And for this, it's useful to go back to this picture I showed you at the beginning, where you were navigating a tree structure. Because the finding we'll basically produce will show that as you move forward for time, you cannot afford to forget about parts of the satisfiability set intersection that came previously. So since you can follow my cursor, let me try to explain this. So let's assume we only remember θ1 and we remember some ball around θ1, like this ball. Then as we move forward to the second task, we may still find an intersection if we encounter this triangle task as the second task. But if we're unlucky and we encounter this other task up here and we just had some circle around θ1 that wasn't large enough, actually the intersection would be empty. So we wouldn't be able to find a solution anymore in everything that we have remembered that would produce a parameter value that satisfies the conditions of optimal continual learning. And that's sort of the intuition that we will be formalizing in this section. So in order to do this, the first thing you actually need to know, or you need to define, is you need to define the smallest informational content in an intersection of satisfiability sets. So for example, in neural networks, you know that multiple neural networks will produce the same function from X to Y. And this is what you're trying to avert here. You're trying to say, well, if the parameters produce the same function, then I will treat them as being part of a redundance class. And we call these redundance classes equivalence sets because they produce equivalent functions. And we define them because perfect memory for us, you're not really memorizing more if you're memorizing two different parameters that produce the same functions. So we basically want to eliminate redundancy in our definition of perfect information. And this just gives you the formal definition of these equivalence sets. You're basically saying, well, I look at the intersection of all the sets which contain the value θ. And so, for example, I don't think this is a particularly good example, actually, this picture for what I want to say. Yes, this is much better. So what this means, for example, if the entire ellipsis you get here is your entire parameter or model space, it could be that actually, even though it's huge, your entire model space can really only discern 5 different functions. And so in this case, you have 5 different redundancy sets, E1, Eθ1, Eθ2, Eθ3, and Eθ4, and Eθ5. And whether you have θ5 or θ5 prime, since they're both in the same equivalence class, it doesn't really matter. They give you the same function. So what we're saying is perfect memory, or what we're defining as perfect memory, is saying you need to have at least one element per equivalence class which has not been ruled out yet by the previous tasks you've observed. And if you want to write this formally, you write it like I've written it up here. You store an element of each Eθ such that that Eθ is still a subset of the intersections, which means that that particular class of functions from X to Y has not been ruled out yet by the tasks you have observed so far. Don't worry about the minimal cover and minimal representation. I don't think we need them for the presentation. And when you have this perfect memory definition in place, you can then basically show that, so this is lemma 4, this is the first result on the slide. You can then basically show that an optimal continual learning algorithm needs to be able to memorize enough to solve the set intersection problem at each time point. So if you actually unpack the lemma, what it tells you is there exists some function which uses the information space and which uses the parameter space and the information space and maps to sets in theta, such that if you evaluate this function at theta t and it, which was the information and the parameter that you fitted to the tth task, you get back some set ct, and this ct set is sort of a surrogate for all the intersections of satisfiability sets so far, in the sense that ct intersected with the next satisfiability set is empty if and only if all previous satisfiability sets intersected with the current one would be empty. So what this means is you get some function which tells you whether or not the intersection decision problem evaluates to true or false. And it's sort of unsurprising, this result, because what we showed is earlier on in the NP-Hardness result is that you can always solve the set intersection problem with optimal continual learning. And so this is the first result, and then you use this lemma 4 in the second corollary, which here I've given you a weak form because it's easier to state. In the paper, we actually give a broader class of conditions that are satisfied more easily. But basically, under mild regularity conditions, any optimal continual learning algorithm will have perfect memory. And to conclude this, I'll give you an example where this actually is the case. Again, it's the linear model. It's nice. It's very simple. We define it as before. And in this case, the condition that we have to meet is actually, so if we go back to corollary 2, the condition we need is that the equivalent set itself is actually in the set of satisfiability sets. So that means you can find a satisfiability set which is exactly equal to the equivalent set. And in the case of a linear model, this is the case because you can basically construct x and y in such a case that in such a way that there is a unique value theta that solves them without violating the upper bound criteria, which basically tells you you can satisfy this condition. Basically, this is what this does. And so to wrap up, the practical ramifications of this is that optimal continual learning is hard, and by implication, approximate continual learning is hard because you're essentially trying to move from a really complicated intersection of sets to another complicated intersection of sets. And you're trying to do this without just memorizing everything that's happened so far, which is what you would have to do in order to do it without errors. So the challenge in continual learning is to try to approximate intersections of good models and carry them forward through time. And this also explains why it's easier to do this with memorization techniques than it is to do it with regularization techniques. Because implicitly, when you're using a regularizer, you're superimposing a lot of structure, you're superimposing a lot of ideas geometrically, how you would move from one intersection to the next. And in contrast, if you just use a memorization technique, you're not really imposing a lot about how this movement would happen from one intersection to the next. And this is why I also produced this picture here, which should give you this intuition that it's easier, excuse me, it's easier to sort of find a single satisfiability set. So that's what we're doing on the right. We're finding a single satisfiability set, which was constructed from a pseudo task. And that pseudo task is the third task plus something that we remembered about the first and the second task. It's much easier to find a good single satisfiability set that is similar to what we actually want than it is to find a value in the first satisfiability set, which would actually have to be in the small triangle here already in order to end up with a value that still works on the third task. And so to summarize this, our work connects set theory to catastrophic forgetting with a picture that I hope is burnt into your skull forever now, because you saw it too many times during this presentation. And what we show is that in order to avoid catastrophic forgetting and to produce an optimal continual learning algorithm, what you have to do is solve an NP-hard problem, and you actually have to memorize the past perfectly in the sense that you need one of each equivalent set elements. And this tells you that when you work on continual learning, you work on something really difficult. You're working on heuristics for NP-hard problems. And it also tells you that memorizing is probably the easier way out compared to regularization, unless you can make very specific assumptions about the data that you would be encountering, in which case regularization may work much better. Anyways, that's enough talking from me, and I hope this was interesting to you, and I'm happy to discuss anything that is still left open, answer questions, or hear your thoughts on the more practical side maybe of these algorithms, of which I have frankly not very much experience. So thank you very much for your attention.
Thank you, Jeremias, for your great talk. I think it was one of the few papers trying to, underline the theoretical aspects of continual learning related to complexity theory. So I really appreciate it, and this is why I also invited you here. So one quick question from my side could be: do you see, apart from this idea that you already mentioned, that memorizing things is the easy way out, do you see other possible approaches that may be really revealed as useful in continual learning? For example, something that popped in my mind as I was listening to you was the idea of using some kind of meta learning to try to learn over time how to piece together these different puzzle pieces that you mentioned, and that maybe could be a way to address the problem.
Yeah, I know scarcely little about meta learning, unfortunately, but while I was working on this work, one thing that popped into my head a lot was if you're happy to make assumptions on what your tasks actually look like. So if you're happy, so the set Q is actually the crux. So if you remember actually all the definitions, we can do what we do here because we're assuming Q can be any empirical distribution. And if you could make a reasonable assumption on what your data generating mechanisms look like, which aspects of them are allowed to vary, these results may not hold. So what that tells you is if you can be strict, if you know what problem you're trying to solve, essentially, so you're not going to have a free lunch. In some sense, this is like a no free lunch result. But if you know which problem you want to solve, you may well be able to find something very elegant. But I don't think anyone's really done that. People haven't sat down in continual learning and thought about my data generating process is allowed to have the following features, and then I'll try to do something with that. For me, but that's how I think, because I come from statistics, so that's usually how we think about these problems. For me, that would be the natural way to combat these negative results. I don't know. I don't know enough about meta learning to answer that part of the question, unfortunately.
Well, thank you. So we have a question in the chat, I think, and then also there's someone with the hand raised virtually. So maybe we can start with answering the chat question.
Yes. Hello, Ola. I'm afraid I don't know what NTM means. I'm quite illiterate in some aspects of machine learning, so you may have to educate me here. Neural Turing machine. I also don't know what a neural Turing machine is. Maybe if you can just speak up and explain what it is, maybe I can answer the question.
No worries. Maybe we can, in the meantime, that Ola is gearing up, we can answer the follow-up question from.
What happens if I allow sufficiently old sets to be removed? Yeah. So what would happen? So let's say you keep track only of the last k sets, then you would have you could define a k optimal continual learning algorithm that only is optimal on the last k tasks. So I guess your question is whether the results would still hold, whether I still get the hardness result. And that is a good question. Let me think about that really quick. So it would depend a bit. It would depend on the sets of it. Because so, yeah, it would depend. So if I think in general it would still be NP-hard even if you only consider the last k sets, so long as the satisfiability sat q doesn't. It's just once, like it's all the satisfiability sets individually. So if your satisfiability sets would be, for example, containing the polytopes, you would still have the NP-hardness problem. As for the perfect memory result, yes, I think that would also still hold, in the sense that I'm not so. You might need some minor modifications in order to formally show it, but my intuition would be that the results hold for even if you only want to be perfect on the last k tasks. Which also, this is another thing I didn't mention. The limitation of this work is that the cutoff is very sharp, right? It's like 0-1. So the 0-1 cutoff also sort of makes things harder in some ways. So you may well be able to perform much better in practice with only memorizing the k last sets if your criterion is not a 0-1 criteria, but if you actually use the kind of criteria people would be using in statistical learning theory, where you allow for certain, probabilistic upper bounds and these kind of things. And in fact, I think there are now, I saw a paper recently on arXiv on a generalization bound for continual learning, but there actually your bound grows linearly in time. So like you suffer similar problems, you use a completely different language than the language I've used here, but you're sort of replicating the same problems, which is that as you move forward through time, things get worse and worse and worse. And that problem would also persist in that other language as you remove older previous sets.
Yeah, that was a particularly interesting question because we often think at continual learning, especially over an infinite number of tasks, in a way that after a while we are allowed somehow to forget about previous things we have encountered if we not encounter them again. I think it's also natural behavior we do as humans. And so that was interesting. So we have a follow-up question from Kelly and then Dario.
Does sweeping these tasks create another task? I am afraid I don't really understand that question. Maybe that's a jargon problem. What is sweeping in this case? Let me answer Dario's question in the meantime, if I can. Are the polytopes the satisfiability sets for the linear regression model used to solve a set of tasks? Are the polytopes sets of tasks? Yes. So I think if I understand your question correctly, the answer is yes. So if you're asking me if the polytopes are the satisfiability sets associated with the linear regression model, then yes, if your criterion looks like the criterion I've showed you. So this example is constructed in such a way that the linear regression case recovers polytopes, and in order for you to do this, you have to choose this optimality criterion. So for example, if this were the square instead of the absolute loss, your sets look different because now they're the balls. Intersecting balls is actually harder than intersecting polytopes, but nobody's even really bothered like proving that intersecting arbitrary balls is harder, because a lot of the literature of intersecting sets has a very limited use case in practice, right? Because ultimately, if you look at the literature that proves set intersection problems, they want to usually use these things for something in computer science. And you wouldn't usually try to intersect balls, but you often try to intersect polytopes. So there are a lot of results for polytopes, which is why I've chosen this criterion. But usually in linear regression, you would probably choose the squared loss. The squared loss would produce balls rather than polytopes. So it's a good question. Linear regression as I've defined it here, with that particular optimality criterion, would indeed produce polytopes. But with another optimality criterion, it may not. I hope that answered the question. But let me know if I completely rambled off about something that wasn't your question at all.
All right. In the meanwhile, there are two people with their hands raised. So, Hola, can you speak now?
Yeah. Okay.
Right.
So, the question on NCM. Can you hear me?
Yeah, I can hear you. Hi.
Oh, okay. So, an NCM is just like a neural net with a kind of extended memory. Where you have a kind of a controller that interfaces with the outside world, it kind of select what inputs you write to the memory, like an LXTM or anything like that. So I was just thinking, is it something you've considered, like if we could put it in the second? Because I think you mentioned memorization.
Mm-hmm.
Like it's better off when you try to regularize or do some kind of heuristics, and so I was just thinking about if it's something you've thought of, or if you could share some thoughts on that.
Yeah, I don't know that particular architecture. I can share my general thoughts on the sort of architectures I have seen with memorization. So, for example, I think there was one paper which used variational Bayesian inference. Oh, what's it called again? Variational something. I'm sure you all know the paper I talk about. Variational continual learning. So that was the paper. I think it got a lot of attention, and I actually think the reason that this paper, well, not the only reason, but one of the main reasons that this paper worked so well and got so much attention is that they were using data summaries transported forward through time. What are they called again? I think core sets or something like this. And this is essentially a form of memorization. So similarly, I saw another paper at, I think, iClear that used Gaussian processes, and that they also performed very well. And the reason they performed very well was that they were again trying to use the inducing points in a Gaussian process essentially based on a memorization strategy. So once again, the trick was not so much the fact that they were Bayesian, in my mind, was not so much the fact that they went the Bayesian way, even though as a Bayesian statistician, I'd like to believe that it helped. But I think the main trick was to actually memorize parts of the parsed. So I think there are algorithms that already sort of encode these engineering features. I don't know the particular algorithm that you were referring to, so I'm afraid I can't answer a question specific to that one. But if it does something similar, then I would expect it to perform well in practice.
Okay, thank you.
No worries. This is actually, in general, something I didn't mention at all during the talk, but all that we're saying here applies to Bayesian models alike. So there's a way in which you can see this. If you look at this parameter theta t, we haven't actually said which space this parameter lives in. If you're doing Bayesian inference, your parameter is a posterior. It's an infinite dimensional parameter, but you can think about it just as another parameter that you're trying to optimize. So all the results you saw, I've defined it all for point estimates because it's easier, but you could do all that you've seen today with any Bayesian continual learning algorithm as well.
All right, so we have another question from Antonio Carta that raised his hand. I don't know if that's a mistake or right.
Yeah, thank you for the talk. So I have two questions actually. The first one is about what can we do to simplify this problem? Because you talk about the model architecture, and you said that linear models are already too difficult to solve the problem. So on that side, maybe it's better to leave it as it is. But you said that we can put some assumptions on our data. And I'm wondering if we can also change our optimality criterion to make it easier to make intersections. For example, even taking an over approximation of the optimal set to make it easier than to do the intersection.
Yeah, I think that's totally fair. Like I was saying earlier, the sharp cutoffs in those sets is something I need for the maths to work. But in practice, I mean, you don't care if if it's epsilon or epsilon plus delta for some arbitrarily small delta. You don't really it makes no difference for you. So in practice, of course, these sets wouldn't really be hard cutout sets. They would be very fuzzy. I don't know whether there is a notion of fuzzy sets. I'm sure it exists. Yeah, it's hard to say. So I don't know whether this is the most interesting way of studying the theory that informs the next generation of continual learning algorithms. I think you're more likely to find inspiration for how you should design theoretically, you should design continual learning algorithms with theoretical guarantees by using statistical learning theory to study them. I was mentioning this one paper that looked at regret bounds. I think that's a very promising avenue because regret bounds essentially do what you were saying. They look at a more fuzzy notion of being away from where you want to be. This is very static, but what that allows you to do, of course, is get all these computational results that you can't really get with the statistical learning literature. So the way I think of it is it's very much a complementary approach. We're looking at two different problems. So for actually solving the continual learning problem, I totally agree with you. You would want to have some notion of fuzziness about how a particular value is. So the very notion of set intersections may not be the most helpful for finding algorithms that work in practice, if that makes sense.
Yeah, makes sense. And this is connected to my second question, which is, do you think that Bayesian method can help? Because I mean, I don't know about regret bound, but seeing your presentation, I thought about Bayesian methods because with Bayesian models, instead of having a point estimate, you can keep the entire distribution, and then once you have a new task, you update the posterior distribution of your parameters, right? So in some sense, you are solving the intersection. I mean, then it's still really hard to update the posterior maybe, but they are doing the same, they're solving the same problem from a completely different perspective.
I'm very partial to Bayesian inference because I'm a Bayesian statistician. So yeah, I will obviously say yes. I believe it'll help. Of course, there are drawbacks to Bayesian inference, particularly when you come from the computational angle, which is a major factor in continual learning to begin with. Conceptually, I always think Bayesian inference is more elegant because it's essentially a way of aggregating multiple models, right? So, I mean, one of the difficulties in continual learning is finding the one model that fits all your tasks. What you're doing when you're doing Bayesian inference is essentially weighting multiple models. I mean, that's really all it is. And that's why I would think, in general, I think, yes, I would believe that it's easier to find something that works with Bayesian inference. It's more forgiving, maybe, about being a bit sloppy with how you handle previous tasks. I'm not sure, you know, being Bayesian alone won't fix things, but I think it's probably one ingredient that will be helpful in designing more robust continual learning algorithms. I think that there's also empirical evidence to suggest that, if I'm not mistaken. So I think so, but I'm not an expert on the actual algorithms. So you should probably ask Vincenzo. I think he knows much better than me.
Thank you.
Maybe we have time for one last question, if there is one. All right, I guess we're done. So thank you so much, Jeremias, for your talk today. I invite you to post your slide on the forum topic that I have already set up on our forum. I give you the link afterwards. And I invite all the other people here in the audience to join our next reading group session next Friday. At the same time. So thank you all for joining today, and then see you then. Bye.
Thank you very much for having me. Take care. Have a nice weekend. Bye-bye.
You too.